we learnt that in redox reactions, transfer of electrons takes place. For example, if you look at the ionic reaction between sodium and chlorine, it is clear that sodium loses an electron and chlorine gains an electron to form sodium chloride. But how does one determine an electron transfer in the formation of a covalent compound like water? In the formation of water from its elements, we can assume that hydrogen and oxygen atoms are undergoing a change from neutral state to positive and negative state respectively. This we can predict is due to the transfer of an electron from hydrogen to oxygen. Unlike ionic bonds, a complete electron transfer does not occur in covalent bonds. Instead, there is a partial transfer of electronic charge. This is known as an electron shift. In order to track the electron shifts occurring in covalent compounds, scientists came up with the concept of oxidation number. The oxidation number method always assumes that there is a complete transfer of electrons from a less electronegative atom to a more electronegative atom. For example, in the formation of water molecule, it is assumed that there is electron transfer from hydrogen atom to oxygen atom, and hence hydrogen gets oxidized and oxygen gets reduced. Note that the electrons in a covalent bond don't really get transferred. It is only a hypothetical assumption made for the purpose of understanding redox equations. Oxidation number is defined as the charge or the apparent charge that an atom in a compound or ion would have. If all the electrons in its bonds belonged entirely to the more electronegative atom. Oxidation number is also referred to as oxidation state. We will be using the term oxidation number throughout this module. To determine the oxidation number of an element in a compound or an ion, certain rules have been formulated. Let's look at these rules. The first rule is that the oxidation number of atoms of elements in their elementary states and allotropic forms is 0. For example, each atom in H2, O2, Cl2, O3, P4, S8, Na, Mg, Al has oxidation number 0. The second rule is that in neutral compounds, the sum of oxidation number of all atoms is 0. For example, in H2O, the sum of oxidation numbers of hydrogen and oxygen atoms is 0. The third rule is that in case of the ions that are composed only of one atom, the oxidation number is same as the charge on the ion. For example, the oxidation number of sodium ion is +1, magnesium ion is +2, ferric ion is +3, chloride ion is -1 and oxide ion is -2. However, in complex and polyatomic ions, the algebraic sum of the oxidation numbers of all atoms in the ion is equal to the charge on the ion. For example, in the carbonate ion, the algebraic sum of the oxidation numbers of the 3 oxygen atoms and 1 carbon atom is -2. the oxidation number of carbon is 4 and oxidation number of oxygen is -2. So 4 plus 3 multiplied by -2, which is 4 minus 6, is equal to -2. The fourth rule says that in their compounds, all alkali metals have oxidation number of +1 and all alkaline earth metals have oxidation number of +2. According to the fifth rule, the oxidation number of oxygen is -2 in most of its compounds, except in two cases. The first is the case of peroxides and superoxides. In peroxides like hydrogen peroxide and barium peroxide, each oxygen atom is assigned an oxidation number of -1. And in superoxides like potassium superoxide and rubidium superoxide, each oxygen atom is assigned an oxidation number of -0.5. Another exception is when oxygen combines with fluorine. For example, the oxidation number of oxygen in oxygen difluoride is +2 and in dioxygen difluoride it is +1. This is because fluorine is the most electronegative element and has an oxidation number of -1. The sixth rule says that hydrogen has +1 oxidation number when it combines with nonmetals. This is because all nonmetals are more electronegative than hydrogen. But hydrogen is more electronegative than metals. Hence, in metal hydrides, where hydrogen combines with metals such as lithium, potassium, and magnesium, its oxidation number is -1. According to the seventh rule, fluorine has an oxidation number of -1 in all its compounds. Other halogens such as chlorine, bromine, and iodine also have oxidation number of -1 when they occur as halide ions in their compounds. But when they combine with oxygen to form oxo acids and oxoanions, they have positive oxidation numbers. The atoms of transition or d block elements exhibit several oxidation numbers. The table shown here depicts the variable oxidation states exhibited by the transition elements. The highest oxidation number of a representative element is the group number for the first two groups and the group number -10 for the remaining groups. This shows that the highest value of oxidation number exhibited by an atom of an element increases across the period in the periodic table. For example, the valence shell configuration of the 13th group elements is Ns2, Np1. They have 3 electrons in their valence shell that they can lose to obtain their octet configuration. Hence, the group 13 elements exhibit highest oxidation state of +3 in their compounds. The same trend applies to all elements from the 13th to the 17th group. In other words, the highest positive oxidation number for p block elements is equal to the group number -10. Now, let's apply what we have learnt and determine the oxidation number of sulfur in hydrogen sulfide. According to Rule 6, the oxidation number of hydrogen is +1 when combined with nonmetals. In this case, sulfur. Let us assume the oxidation number of sulfur to be X. We will write the oxidation numbers of the atoms above the chemical symbols. If we calculate the sum of the oxidation numbers of the atoms, we get the result as shown here. According to Rule 2, the sum of oxidation numbers of atoms in a neutral compound is 0. Therefore, we will add 0 to the equation. As per the equation, the oxidation number of sulfur in hydrogen sulfide is -2. We learnt that certain elements exhibit more than one oxidation number. For example, the oxidation number of copper in Cu2O is +1, while the oxidation number in CuO is +2. How is the oxidation number of such elements indicated in a compound? Alfred Stock, a German chemist, introduced a nomenclature system to indicate oxidation numbers for metals that exhibit more than one oxidation number. The nomenclature, known as Stock notation, indicates the oxidation number by placing a Roman numeral within parentheses after the symbol or name of the metal. Thus, the oxidation numbers for copper in both compounds can be indicated as shown.